linear functions and linear regressions. We've been looking at functions in general. Now we're going to look at specific functions in more detail. We're going to begin by looking at linear functions and linear regressions. You've looked at polynomial equations in the past. A polynomial function is either 0 or can be written as a sum of one or more non-zero terms. For example, if we have the function f of x equals 3x squared plus 4x minus 7, the leading coefficient is going to be 3, and the degree of the function is the highest exponent, or 2. So with polynomial functions, we can have a zero function where f of x equals 0, and the degree from this one is going to be undefined. We have a constant function, f of x equals a. For example, f of x equals 3. It's a constant, it doesn't change, and the degree is 0 because we could have 3x to the 0 in that case. A linear function, f of x equals something times x plus b. So we could say f of x equals 3x plus 7. That's an x. The degree there is going to be 1. We have a little imaginary 1 there, so our degree is 1. And then quadratic functions we will be looking at a little bit later. We have some number times x squared plus another number times x plus c, and the degree will be 2. To find an equation of a linear function, if we are given f of negative 1 equals 2 and f of 2 equals 3, we have 2 points. This is our x, and there's another x, and those are our y's. So essentially we have 2 points. We have negative 1, 2, and 2, 3. So if we're going to find the equation of this, we want to find the slope. So m is equal to 3 minus 2 over 2 minus negative 1, which is 1 over 1/3. And then we'll put it into the point slope equation. And at this point we can use either equation, and I'll use the second one just because it doesn't have a negative. Y minus 3 equals 1/3 x minus 2. And depending on how the question is stated, you can leave it in that form, or you may be asked to multiply it out. This would be y minus 3 equals 1/3 x minus 2/3, and then we want to add 3, and we'll add 3/3, so we get y is equal to 1/3 x plus 1/3. Try this one. Write an equation for the linear function g such that g of negative 3 equals 5 and g of 6 equals negative 2. The average rate of change. The average rate of change of a function, y equals f of x, here's our general function, between x equals a and x equals b. These are just values. It could be, for example, x equals negative 3 and x equals 4, would be f of b minus f of a over b minus a. In previous courses, you learned this as the slope equals y2 minus y1 over x2 minus x1. So translating that, here's our y2, here's our y1, and here's our x2, and there's our x1. Different terminology, same idea. A linear function will have a constant average rate of change between any 2 points. The average rate of change is the slope. So all that means is if we have a linear function, for a linear function we have a straight line. And so any 2 points from here to here or from here to there, the rate of change will be constant, or the slope will be the same. Looking at the nature of a linear function, there are 4 different ways. We can look at it verbally. What's the degree of a function? If it's a linear function, the degree is going to be 1. We could look at it algebraically. What's the equation in slope-intercept form? We can look at it graphically. What does it look like when you graph it? And we can analyze the function. We learned how to use the graphing calculator to make a scatter plot. We've learned how to compute a regression line and put that regression line onto the scatter plot. We're going to look a little bit deeper into the regressions at this point. We have 5 different kinds of scatter plots. When points of a scatter plot are clustered along a line, we say there is a linear correlation between the quantities represented by the data. When an oval is drawn around the points in the scatter plot, in general, the narrower the oval, the stronger the linear correlation. When the oval tilts like a line in a positive slope, the data have a positive linear correlation. If it tilts like a line with negative slope, the data have a negative linear correlation. And some scatter plots have little or no linear correlation. We have a number that represents the strength and the direction of the linear correlation, and we call that the coefficient R. R will be between -1 and 1. When it's greater than 0, there's a positive linear correlation. When it's less than 0, there's a negative linear correlation. When the absolute value of R is approximately 1, there's a strong linear correlation, and when the absolute value is approximately 0, there's a weak or no linear correlation. And we're going to be looking at this a little bit more in class. So the steps of doing a regression analysis is to enter and plot the data, which is making the scatter plot. We find the regression model that fits the problem situation. Is it a linear regression? Is it quadratic regression? We put that graph onto the scatter plot and look at how well it fits, and then we can use that model to make predictions. Now I leave you just for fun. See you in class.